Well, hello, my friends. This is Jeff Curtis coming to the mountains, or coming from the mountains to you again, on behalf of the Theosophical Lodge, and I'm happy to be with you again, and just take a little tour of some latest thoughts and ideas in science that I want to share with you uh, tonight. Um, what we've been talking about and trying to sketch both some details scientifically and then add in some of my own reflections and ideas as a theosophist and a kind of a out there scientist has been nature of space and time. And what are we talking about when we refer to space and time? It's a topic that goes way back to the ancient Greeks, and a great deal of very advanced thought happened at the time of the ancient Greeks. A next big stopping point would be Galileo in the Renaissance period, and Galileo formulated a lot of laws of motion, and we learned about very fundamental things like velocity and acceleration, and he did experiments with inclined planes and watching things roll, and he discerned a lot about the laws of motion in what we would call a Euclidean or a flat space-time. That is, uh, uh, assuming that space operates the way you learned about geometry in high school, which is Euclid's geometry, where two parallel lines will never meet, ever. And we can just apply the simplest view of what space-time is. It's kind of an infinitely big object that, or space that we can put things in and measure distances from one thing to another, and that's what we need to describe what's going on, as well as maybe a watch that clicks and measures off time for us. And gee, all watches would be the same, right? A watch held by me here would click at the same rate as a watch on a train that was going by, right? There's no real reason to think time would be different for stuff moving around in Euclidean space if we're doing experiments on the size scale of human beings and planet Earth, let's say. Um, so those laws of motion and ideas, including the seeds of the idea of relativity that Galileo put in motion, and later he got in lots of trouble for inventing a telescope and upsetting the clerics of the day. But his laws of motion didn't upset anybody. The people were cool with him just being a quiet early physicist working in the laboratory, measuring how fast things moved and how they moved. Well, those laws of motion that were encoded by Galileo stood as a huge achievement and were used by people trying to extend physics. And then along came Newton, Sir Isaac Newton, in the 1700s, and he was arguably the greatest scientific genius ever. If you just measure how much progress did one person do and make in terms of understanding how the world worked, Isaac Newton was astounding. Along the way, he invents calculus. He invents the Newtonian telescope, which is the design of telescopes we use now. That James West Space Telescope that's sending back all the incredible images from outer space right now, following the design of the Newtonian reflecting telescope. Um, I could go on and on about Isaac Newton, but to project on, then extrapolate onto the next big genius that upset everything and changed our concept of the world would obviously be Albert Einstein. So these last couple of lectures to you, I've been speaking a little bit about the theories of Einstein, and I realized that I've been going back and forth a little bit between the two different cases of relativity that he invented and had his insights to. And since this is a non-specialist crowd, I think I want to just drop back a little bit from where I was last time. And I want to underscore the difference between these two basic types of relativity that Albert Einstein came up with. The first one, and there was a year, 1905, which many people refer to as Einstein's miracle year. That was the year when Albert Einstein, this amazing genius, figured out three huge things. He published three papers that changed the face of science forever. One of them was on his theory of special relativity. So special you can think of as the first case or the simplest case of his theory of relativity. The other two papers also very interesting. One of them had to do with the photoelectric effect and the way in which light bounces electrons off of materials. I teach about that in a very detailed way when I am teaching chemistry classes, because this is the place where we learned that light comes in quanta of photons and interacts with matter, and that light energy can show up as the energy of an ejected electron after it hits a material. And so Einstein was able to, that combined with the work of Max Planck, start the whole quantum revolution. It took off from there. The other paper that he published had to do with Brownian motion of dust grains as viewed through a microscope. He was able to mathematically analyze that and come to a firm proof of atomic theory. Because in the early 1900s, not everybody was yet on board with atomic theory. They weren't quite sure what the constituents of matter were. Well, Einstein proved matter is composed of atoms that are moving around and jiggling and bouncing and doing weird stuff, and he could prove that using statistical inferences by the way pollen grains moved in a drop of water, believe it or not. Don't ask me to go to the board and show how he did that. I would have to study up on it for days before I would have a clue. The other one, the photoelectric effect, I am pretty familiar with. The one I want to talk about now is the special relativity. And this is the one that then impacted on our sense of space and time. Newton, as much as he did in refining Galileo's work on the laws of motion, and Newton brought in all kinds of deep insights having to do with rotating objects and accelerations and how can you predict the exact trajectory of a cannonball after you fire it. All that, Newton did all that, but he stayed within the confines of a Euclidean space-time, meaning a flat space and time, as was used by Galileo, although in a less ornate fashion than Newton did. Well, Einstein busts that up with his relativity paper, Special Relativity, in 1905. Okay, so what was that about? What I'm going to do here tonight is drop back and just explain that a little better and show you one crucial result mathematically that comes out of it that you may have heard about and know about. And I'm hoping that by the time I get done here, you'll have a little better sense of at least one of the mathematical results of special relativity that'll make sense to you. Okay, so similar to the laws of quantum mechanics, in order for Einstein to develop and elucidate the laws of relativity, he had to assert two basic postulates. In quantum mechanics, we have more basic postulates, and people are trying to come up with new and better ones all the time. So the whole field of quantum mechanics, as you've heard me talk about it here a few times, that grows out of making a set of 8 or 9 different postulates and then proceeding to erect a mathematical framework and see how well that matches up with reality, and thereby arrive at some degree of agreement as to what the mathematical structure of quantum theory looks like. Special relativity flows from just 2 postulates, but they're important, and it's worth mentioning what these things mean and what the language associated with them stands for, so that I can then talk about this in a little better way than otherwise. So the first postulate of special relativity, which sounds kind of obvious, turns out to be hugely important, is to postulate that the laws of physics, meaning really just the way stuff works in a local environment sitting in front of you, will be the same in all inertial frames of reference. Okay, now that's the thing I need to define for you a little bit. An inertial frame of reference is, imagine a coordinate grid. You can think of the coordinate space-time grid, the way that we often signify those is to draw a coordinate grid like this, where we might have the z-axis up, the x-axis coming out, and the y-axis going that way. So this would specify a point in space. This coordinate grid, that's all I'm talking about. If we, there we go. So that coordinate grid, if you just think of one of those with its origin point moving at a constant rate in some direction, now that's important, moving at a constant rate, that defines what we call an inertial reference frame. It's either at rest as a coordinate grid, distances in height, lateral, and depth. Those can be rotated any way you want, it doesn't matter. But if it's sitting at rest or moving at a constant velocity, then it's called an inertial reference frame. That's a hugely important concept in relativity, constancy of motion. And that's what's special about special relativity, is that it presumes constancy of motion. Now, the second assumption is, and this was the big leap, this is the blockbuster that nobody else had lit upon before, but Einstein did, and it ended up being the key that unlocked everything, was to assert that there's something special about the speed of light. And the speed of light will be the same speed in all directions for all reference frames. And that the number speed of light turns out to be 300 million meters per second. So that would be 3 times 10 to the 8th meters per second. 300 million meters per second. That's an easy number to remember if you say it enough times. That speed of light, it's the same whether we shine a flashlight beam from a steady origin frame at rest or one that's moving at some velocity in another direction. And the reason has to do with a property of space-time. And we could think of that property as the space-time interval that defines causality. So the speed of light is really not as much about light itself as it is about the maximum rate of causality, the maximum rate at which our space-time substance, whatever it is that we're embedded in, will allow one event to influence another event directly, at least by known physics that we're aware of. And that means sort of modern materialistic scientific physics. I don't want to go here into realms of psi effects and telepathy or clairvoyance or the kinds of super interesting stuff that we like to think about all the time as theosophists, and we care about those things. But I'm gonna crunch down to a narrower kind of measurable reality that any old dude like me in a laboratory can replicate lab to lab. The maximum rate of causality is the speed of light, and it's independent of motion or direction or acceleration or anything else. Now, why that should be is not obvious. It took a mind like Einstein to go there and to figure that out. But what that all comes together as and informs us about is the primacy of something we would call a space-time interval. So a space-time interval is kind of like a distance in a Euclidean space. You think about distance in a Euclidean plane, so just a plane, x and y axes. The distance between 2 points is easily computed with a ruler, and if you then draw a right triangle to that ruler, you'll get a short side and a long side, and you can do the Pythagorean theorem, and you can compute the distance between any two random coordinates as solving a Pythagorean triangle, a right triangle, in a coordinate grid based at the 90-degree point of that triangle. I don't have a picture for you defining that. I'm hoping maybe you'll kind of remember it from the old days. But that space-time interval has a form. I'm going to show it to you here, which is there at the top of this piece of paper. So the space-time interval turns out to be equal to c times delta t squared minus delta x squared minus delta y squared minus delta z squared. So what is c times delta t? Well, that would be referenced to this drawing. So here's the drawing that we use. This is called a space-time diagram. And I just made this up to illustrate for you the next point I want to get to. But for now, just focus on the axes. So you can see that along the horizontal, I have an x-axis that runs from 0 out in the x direction. And if you can read them, you'll see that I've set this up so the units are 2 squares per unit, and it goes 1, 2, 3, 4 off to the side there. The vertical axis takes a little discussion. The vertical axis is the time axis. But in order for these diagrams to make sense, we renormalize our idea of time, and we draw the units of time in units of speed of light, c, times time in seconds. So we know that speed of light, 300 million meters per second, times time in seconds. We're going to now express time in units of meters, and as far as the amount of time it takes for light to go, 300 million meters in a second. So our unit of time here is different than a second. It's a second multiplied by the speed of light. So our unit now is proportional to time, but it's scaled in a way that allows us to draw these space-time diagrams in a particularly friendly and rational fashion. So that's where we're at. Now, I went through all that to then start simplifying it. So you'll see that the way that the space-time interval is defined, it's got the units of distance of x, y, and z. Well, let's forget about y and z. Let's just think about one dimension of space. So now our container is a little simplified. It's a plane. Things can only move along one axis, which is the x-axis. That allows us to then go about and start understanding special relativity at the next level. So one of the key things that we need to understand is that between any two events in space-time, the space-time interval will be independent of coordinate system you use. So, or that means inertial axis, inertial frame of reference. So observers can live in frames of reference. Those frames of reference are either moving at a constant rate or they're stationary, all right, in the confines of special relativity. And any two events or points in this space-time thing we're constructing will have the same space-time interval as computed using that formula I gave you there. Now, we simplify it down. This is going to allow me to prove something to you that you may have heard about. And it's the stuff of science fiction stories. And we're just going to shortly go through this, and you'll see some numbers. And you'll understand a little deeper where some of the science fiction or more out there fiction you've read about comes from. So you might have heard of something called the twin paradox, or relativistic effect on a traveling friend or a traveling twin, what have you. And so the scenario is this, and you may have heard about this, which is that if your friend gets on a spaceship and zooms off into space in some direction for however long, turns around and zooms back, your friend will look to have aged less than you did. In fact, if they go far enough, fast enough, maybe they've only aged a couple hours and you've aged for years. And that notion finds its way into lots of fun, interesting sci-fi stories and stuff. Well, where does that come from? It turns out that comes from the special law of relativity, having to do with constancy of space-time intervals and the fact that time is plastic. Time is stretchable. Time isn't a constant thing. The thing that's reliable from reference frame to reference frame is the space-time interval, not the exact amount of time involved in something. So how do we illustrate this a little bit? First of all, let me say that another way to think about this trippy little diagram. If you look at that vertical axis, CT, we're all moving through time at a rate which is the maximum possible rate, which is to not move in the x direction and to just move vertically along the z-axis there. If you just stay in one place, time, it forces you to move at the rate c times t along this z-axis that we have created. All right, let's think now about the space-time interval traveled by a person who stays at home on planet Earth and their twin or their friend who gets on the spaceship and goes off to the distance, turns around and comes back. We're going to illustrate that scenario by two different pathways on this figure. So one person stays at home and just travels up the z-axis, right like that. The other person goes off in the direction x for a period of time and then turns around and comes back to the origin point and returns home to Earth. Well, how could it be that their age is any different? It turns out they have traveled different space-time intervals. That if you're the one who is at home and you stay on the vertical axis there, and you're just not doing anything, you're still traveling through time at the maximum possible rate. The person who went off a certain distance has a different space-time interval than you did. Let's compute those because it's easy to do. So first off, I'm sorry for the awkwardness of this. Maybe one of these days I'll get better at it. But as you can see, the twin who stayed home traveled 6 units of time vertically, 6 units of CT. If you solve the space-time interval where delta S squared is equal to delta CT squared minus delta X squared, and then you get a number of 36, and then you take the square root of that, what you compute is that the person who stayed at home traveling through time at the maximum possible rate traveled the square root of 36, which is equal to 6 units of space-time interval. All right, what about the person who went off in a certain direction and then came back? So that means we're going to travel along x by 2 units and we're going to travel a long time by 3 units and get to point R, which is the turnaround and return home point. Well, if I go through the algebra there, I find that one leg of that trip, let's just take it from the origin to the point R, involves space-time interval square root of 5 by just cranking through the algebra. We did it twice. We traveled away at some velocity and then we traveled back. Let's just assume it's the same velocity. It doesn't really matter. So that means the total space-time interval traveled is twice times the square root of 5, which comes out to 4.472. I don't expect that you sat there and pounded it out on a calculator. I did it twice. I'm pretty sure it's right. So, whoa, what's up with that? My friend who went out there some distance, turned around and came back, evidently traveled a shorter space-time interval than I did by just sitting here at home. It's because we move our fastest rate through time when we don't move in space. That is one of the massive insights that Einstein came up with. And this mathematics was designed to capture that fact. So what's another way that we could say this? We could wrap our language around the sequelae of these events. Well, we might say that this whole thing that I've just described there is only possible if the moving twins' clock slowed down. Had to slow down by an amount, 4.72 over 6. Turns out to be about 75%. Your friend or twin on the spacecraft doesn't know that, because remember the first postulate we had, that clocks moving on inertial reference frames are governed by the laws of physics. And I said one of the postulates of special relativity is that the laws of physics are the same for all inertial reference frames. That means that something you would build like a clock would work the same in all inertial reference frames. That means that what's called the proper time, we could just think of it as the local time, or the time which somebody experiences, stays the same. It's perceived as being the same for everybody, no matter what their state of motion, as long as it's constant motion. And so it's not like the traveling twin experienced time in a different way. As far as they could tell, the physics of their clock were still fine, and their clock was running at the same rate as it did for everybody else. But lo and behold, they get back to Earth, and not much time has passed for them, and has for you. Let's say this experiment is done on the time scale of a day or so. What you might see is, both men, is that one person, the person who stayed on Earth, would have more than a 5 o'clock shadow going on, whereas the person who did the traveling would still be clean shaven, let's say, if we started this experiment off with both twins shaving their face in the lab. That's pretty weird, and it's only possible if time stretched out, meaning that the clock slowed down for the twin who was traveling. That's what this all proves. Another word we use for this is time dilation. We would say that time dilated for the twin who was moving, and we can compute the amount of that. The time dilation factor would be 1 over 0.745. So there's a time dilation of 1.34 involved here. So how weird is that? It's been tested. It's been tested out the wazoo. People have figured out ways to test this. Well, the best ways we can test this really is to take radioactive isotopes that decay with a certain known rate of decay and speed them around in accelerators and stuff, and see how the lifetime of their decay rate stretches out relative to us stationary observers. So those big particle accelerator rings, or let's think more obviously of the linear ones, because there's the Stanford Linear Accelerator, for example. You can prove to very, very high degree of precision when you send electrons or really any other elementary particle down a straight pathway at something approaching the speed of light, time stretches out for them as viewed by us. In other words, their clocks slow down. And this experiment can be done with arbitrary degree of precision, and it comes out correct time after time after time after time, which is just astounding. And then leads us to cracking our heads open and seeing space-time as something deeper and more complex and more interesting than what immediately meets the eye. It does immediately meet the eye if you're a smart enough physicist and you know how to design the experiments that elucidate this property of space-time. But those kinds of experiments didn't become possible until early in the 1900s. Now, this is an interesting example where the key insight and the mathematical leap into a new kind of physics actually took place in Einstein's head before the instrumentation could catch up with it and test it. That's fascinating. Einstein got all the way through this math and understood everything I just explained to you about time dilation before it was testable. But it soon was testable, which is pretty amazing, an interesting coincidence. That means that these ideas were already in play. And in fact, the ideas of relativity were in play with a fellow named Lorentz, for one. There were coordinate transformations, and this form of a space-time geometry had been invented by a fellow named Minkowski. So the mathematical structure was there. Beginning inklings were there. It took an Einstein to come along, tie it all together, have the crucial insight that the speed of light is actually about something more fundamental even than light. It's about causality and the way in which events move relative to each other depending on the rate of motion. So that came together, and we ended up with a whole new way of looking at reality, which was soon tested and verified. Okay. I want to go back and just tie the echo before I close here. Remember, I started off saying that quantum mechanics, as weird and wonderful as it is, rests upon the interplays of, depending how you write them out, call it eight solid postulates of quantum mechanics. These are things that have to be true about reality. We do experiments, we test it, see if they work, come up with better math, and there's an interplay for a while between the experiments and the postulates, and finally what emerges is a consistent mathematical structure in view of how reality works, and the ability to predict and explain, well, not completely explain, let's just say map, describe, and to some extent predict what experiments will do in the lab. Can you see the similarity there? Postulates leading to a mathematical structure which you then test against reality. That leads to a refinement that comes back. This is the way in which relativity has progressed, and it's the way in which quantum mechanics has progressed. And it's particularly interesting, sort of inspiring, because there's intuition, there's beautiful guesswork, well, maybe it works like this. Put in another postulate. See if you can then from that create a mathematical framework that hangs together consistently. If you're enough of a genius, just a consistent mathematical structure is enough to convince you that it's real, which is what Einstein did. So, all right. I think I'll close upon that and let you think about it a little bit. And I think in our little series of talks here, we'll have at least one more where I'm going to, from here, having talked about special relativity, then return a little bit more formally to and get a little more of the nitty-gritties of general relativity. So general relativity is the one that has to do with how matter bends space-time and creates curvature in space-time. That's where we see the interplay between gravity and time dilation. For example, if you ever saw the movie Interstellar, where the people go down to the surface of a planet that's in the gravity hole of a black hole, and it's this weird gravity environment. Oh gee, every hour here is 3 weeks at home. We can't dally too long. Well, that's a general relativity discussion, which is not what we've had tonight. But we'll loop back around to that and do so. And it's good to see you folks, and wish you all a great week ahead. Okay. Bye.